halfway between the two. They are held 15 centimeters apart, so 15.152 meters apart, which means this is actually 75, 76, so 0.076 meters, right? Okay. So first thing I'm thinking when I read this problem without seeing the opposite signs is I was thinking that these two would push against each other, so therefore there'd be no electric field in the middle. But since they're opposite signs, I put a positive test charge here, which is what we always envision electric fields being. The first one will be pushed this way, the second one pulled this way, so they're actually additive. And since they're proportional, they're going to be the same magnitude, right? So I can either use the electric field caused by one charge, or I can use my definition, right? So I'm going to go definition first, which is force per unit charge, which is KQQ over D squared over Q, right? I'm going to get to the form we used in a second.
Which is?
Because that's the force, KQQ over D squared.
Yeah, I used that form.
Divided by Q.
I didn't do that.
That's how electric field is force per unit charge, right?
Yes.
So it's dividing out the charge that's in the middle. There's nothing to charge there, so that's good news. So you're going to get FQ over D squared, which is the charge, the electric field caused by one charge.
Why are we getting rid of the second Q?
Because an electric field is the force per every coulomb I put there. What is missing is the coulombs I put there. I can't accommodate for what's there. There's nothing there.
Okay.
Right? There's not even a charge there. We're asking about electric field for something where there's nothing to charge at that spot, right?
Mm-hmm.
Right, here's no charge. Now there's two here, but I can only use the one because this one's causing electric field at that spot. Does that make sense?
Yeah.
Okay, these are the ideas. It's a very common misconception right there. I feel like I need something there. We're talking about a effect on the field there. This effect on there being something there that's not even there. Okay, and so then I would get 9 times 10 to the 9th times 1.8 times 10 to the negative 7th divided by 0.076. Nine exponent 9 times 1.8 exponent negative 7 plus divided by 0.076, and I get a lovely, I got 21,300 newtons per coulomb. Great? Yeah, they agreed? Uh-oh.
21,000?
Did you square one?
I did not, and I should have, so let me divide by 0.076 again. Thank you. How about 280,000?
Sure.
292936.
2929?
I had 300,000.
All right, how are we getting the answers?
I like Colin's answer.
9 exponent 9 times 1.8. Oh, it's 1.88. That's why I'm getting the answer. Negative 7 divided by 0.076 divided by 0.076. Boom. How about 2929? Sounds like something somebody said to me a second ago. Newtons per coulomb. That's caused by one field. What are these things? That's what this charge. I did 9,223,000. No, that's not right either. What the heck am I doing?
It's 292.
So busy rounding, I didn't get my answer. 293,000. How's that?
Yeah.
Okay, that's caused by one.
I'm going to do round it now, though.
The other one's symmetric.
So it's times 2.
Times 2, and I get 5, 8, 6. 1, 2, 3.
Whoa there, negative. Whoa.
Sorry, what?
Negative.
Why negative?
One of these is a negative 1.88.
Right, but when this is negative, it's pulling which way? Keep in mind, the sign they're telling you which way it's pulling, they're not actually telling you a negative force exists, right? So they're both pulling in the same direction, so they'd add up. And have twice the electric field pushing to the right.
Can we do this?
Does that make sense?
I got the same number. 5, 6, whatever.
Would you put a negative on it?
I did 5.
So if I assigned that to be that negative and that positive, it would go to the left, and then we get a negative answer. Since I assigned it, it really doesn't matter.
But you know what charge the test charge.
Well, test charge is always considered positive. Always considered positive. Electric field always drives things in a positive direction. Where a positive test charge would go. What was your question?
Why is the distance negative 0.76?
It's 0.076.
Why is it 0.76?
Because we're talking about halfway between the two is what's the electric field. So if it's 0.152 between the two, halfway between would be 0.076.
That's why I got 14 because I did 15 meters.
The electric field is positive. That means it's pushing.
Because I set this to be positive, it's negative. This first one is positive, so it push it to the right. The first one's negative, so it pull it to the right. Right? Now, if you made this positive, this negative, it would be going to the left.
Can you test this on that? Or
You can't because it says two equal opposite charge. It doesn't tell you which one's which.
so saying it's negative still.
It would be totally correct. There'd be nothing wrong with that at all. It's a magnitude question. They can't actually ask.
There's no like sneaky way you're going to test this on this test.
Here's how you do it, and this is really, really important, so listen carefully. It's a direction a positive test charge would go. So if I give you a negative charge here and ask you what the electric field is at this point, and I ask you for a direction, you would say positive test charge would go to the left. Okay? So that'd be the direction of the electric field. So you can say negative X direction or whatever that happens to work, or east or whatever, sorry, west, or whatever that would be, right? You have to look at the problem and say, opposite charges attract, same charges repel. I'm going to keep track of the signs myself because the formula does a really bad job of this, right? The formula itself is reflective only of when the charges are the same, they're repelled. When the charges are different, they're attracted. That doesn't tell you which direction they go in our usual sense of those sorts of things, right? So you're going to have to be in charge of that throughout this whole entire second semester. You're going to have to look at the real problem and go, which way would that charge go?
But
Okay.
I'm a little confused about these sort of drawings. Why
Right.
don't you draw the arrows from the positive to the negative? When
Because a positive test charge, remember we always treat it as positive test charge, would go which way? That's why.
Even though the electrons are what moves.
Exactly. Thank you, Ben Franklin. Wait, again, over and over and over again. I was listening to a lecture on Sunday from a guy from MIT. He spent 8 minutes making fun of Ben Franklin for torturing students. He said the most evil man that's ever existed in science is Ben Franklin because he made this sign change. Because he got it wrong. He had a 50-50 chance. Or he could have waited till somebody could actually figure it out. But no, Ben Franklin went out there on a limb and got it wrong. And so we have to deal with this. And he was talking very much about this electric field situation. That's wrong. And he was advocating strongly that he was actually advocating that student body should kill all the people over the age of 25 so they could fix this problem. It's that important. It should be a cultural revolution through the event. They are crazy at MIT. They're crazy at MIT. Good?
That second answer is for part B?
This answer?
Yeah.
That's
Or
that's
just
part A.
Part A.
Because they add up, right? The electric fields add up.
Okay, that's it.
The second one would say, what would be the magnitude and direction of a force would act on an electron placed there? So how do I find a force given an electric field?
We do E equals
E equals
S over Q.
F over Q, so EQ equals the force on the thing. So I would just take my electric field,
And then it would be negative?
and I would go, electric field is 586,000 times negative 1.60 times 10 to the negative 19. Something in my calculator.
We use the correct one.
It says, how will be the force on an electron?
Oh,
It's the only reason I'm using it. Shift answer times 1.6 exponent negative 19. And I get the force would be equal to 9.37 times 10 to the negative 14th newtons, right? Now the next question is, it says direction.
It would be
It would depend, wouldn't it? If this was positive and that was negative, the electron would go that way. If this was negative and that was positive, it'd go that way. So how do I answer that?
dependent on the problem.
So how would you say it so that you can answer it no matter which way I set up the problem?
Just towards
Towards the
proton.
positive charge. Towards the positive charge. The electron would have that much force towards the positive charge. Whichever side that's on.
And would it be a negative force?
No, it'd be positive force in that case, because you're talking about which direction you pushed it. Or it'd be a negative towards the electron. Remember that the positive negative sign, you're spinning way too. You're looking at the negative sign going, well, the negative has to tell me something. What did it tell you? The negative tells you it's attracted to the positive. Where's the positive? This problem doesn't tell us where the positive is, so you'd have to say the electron is going towards the positive. That's what the negative sign is telling you. Not left, right, not up, down. It's telling you towards the positive charge. That's what it's telling you. That's what you need to know. And that's the part about this. That's one of the things in EF. There's like 3 or 4 quirks like this where it's kind of your job to look at the problem and go, well, it'd be attracted towards the positive. That's what has to happen. Make sense? Okay, milk and oil drop. You guys remember the milk and experiment? 2 metal plates. Put a little drop in there. It's fun. You should do it absolutely in college. The best experiment you've ever done.
What class would you do that in? So I know to avoid that.
That was my E&M. It was my upper division E&M lab.
So,
To avoid that.
Yeah.
not taking
That
It was what?
that and
Okay, so
Oh,
like
chemistry. Every chemistry lab. Every last one of them. It's terrible. I'm being recorded. I won't use the word. I want you to use there. Every last chemistry lab, man. At the end of it, I was like, okay, I don't care. I don't care. Yeah, it was fun. By all means.